Alrighty, so this video we're going to discuss radioactivity. In particular, we're going to try to find an equation or a model which tells you about how radioactive a particle is, or maybe a better way of putting it is maybe how long does it take for a sample of a radioactive material to decay into smaller and smaller parts. And to do this, we need to know something called the half-life. The half-life is the term that's used for radioactive materials to describe how radioactive a particle is, how quickly it'll decay on average. And what it actually represents is the amount of time it takes for a sample of radioactive material to decay to 1/2 of its original size. And of course, when I say size, I don't mean necessarily physical dimension, like length or height or something, but rather, if you have 10 grams of a sample, how long does it take to decay down to only 5 grams of the sample left? Or if you have 1,000 particles, how long until you only have 500 particles left? So you have a sample, a certain amount of this substance that's radioactive. On average, it takes a certain amount of time based on the characteristics of that particular radioactive particle to decay down to half of its size, which is very interesting because it's not necessarily intuitive to think that this is how things work. For instance, if I were to tell you that the half-life of, let's say, iodine, and let's say it's iodine 131, this particular isotope, is, let's say it's about 8 days. Okay, so the half-life of this particular isotope of iodine is 8 days. That means if you have 1 kilogram of iodine 131 and you wait 8 days, you'll now have 0.5 kilograms. So that means you've lost half a kilogram of this substance. But what's interesting is if you wait another 8 days, so you wait 8 more days, you don't have 0 kilograms, so you don't lose another half of a kilogram. Instead, you will now have 0.25 kilograms. So that's weird, because what it says is you have a sample. If you wait 1 half-life, half of that sample is gone. So if half of that sample is 500 particles, so this would make you think that every 8 days you'd lose 500 particles. But it's not true, because if you wait the first 8 days, you'll lose 500. But then you wait another 8 days, you only lose 250 this time. So the amount you lose is less, but it's always half of what's remaining there. That's why this is called a half-life. So every half-life, no matter how much you have, you'll have half left after you've waited. And then you wait another half-life, half of whatever's remaining, that's left over. And then half of that, and then half of that, and so on down the line. So like I said, at first it's not intuitive. You would imagine if a particular particle takes 8 days, half of them are gone in 8 days, so you'd think, well, every 8 days you'd always lose exactly that many particles. But no, the amount of particles you lose depends on how much you start with. So that leads us to an equation. It turns out that there is, in fact, an equation that allows us to calculate exactly how much of a substance we will have left given we wait an amount of time. And it goes like this. The number of particles we have remaining after we wait a certain period of time is equal to the original starting number of particles times an exponential. And in fact, it's the exponential e to the minus lambda t. Okay, so let me explain some of these things because, of course, it's not necessarily easy to see what all these represent. N is how much you have left. How much remains. So that means T is how long to wait. And naught, that's how much you started with before you waited. Okay. E, that's just the exponential function, and then lambda. Lambda is called the decay constant, and this is the number that is specific to the particular radioactive particle you're talking about. So uranium has a certain decay constant. Carbon has a certain decay constant. And in fact, different isotopes of carbon. So carbon-14 has a certain decay constant. Carbon-12 has a different decay constant. Uranium-235 and uranium-238, different decay constants. Each different radioactive particle has a different decay constant. What the decay constant represents is where the half-life comes into play. And it comes into play like this. Lambda is equal to a number, 0.693, over the half-life. So T to the subscript 1/2 is the way you write half-life. So this is where, as I said, with iodine-131, it's got a half-life of 8 days, so T1/2 is 8 days. Now, of course, you would put it in units of whatever the units of the problem are. You know, are you talking about waiting 10 seconds or 1,000 years? Whatever the unit of time you're talking about, that's the units you want to use for the half-life as well. So you may have to convert 8 days to years or something. Now this 0.693 is a kind of a weird number. It's an approximation. It's actually the natural log of 2. Okay. So the natural log of 2 is about approximately 0.693, and so usually you see it written as a decimal instead of the natural log because natural log looks too very mathematically complicated to people. So this is our equation, and in fact written slightly differently. N equals N naught e to the minus 0.693 times T over T1/2. So all that's in the exponential. And this equation is used usually for a problem such as you have 2 kilograms of iodine-131 whose half-life is 8 days. How much iodine will you have left if you wait 24 days? So in that case, N is what you're looking for. How much will you have left? And naught is how much you started with, 2 kilograms. T1/2 is the 8-day decay constant, or half-life. And T is how long did you wait? I waited 24 days. Notice the half-life and the amount of time waited are the same units of days. They always have to match. Whatever units you use, make sure it's the same units for T1/2 as it is for T. And this is a very, very nice equation. This allows you to predict exactly how much you'll have left. It also allows you to figure out, for instance, let's say you're a medical physicist And as you learn in a different class, physics of medical imaging, one of the modalities of imaging is PET scans, positron emission tomography. And with this, generally speaking, a radioactive fluid is pumped into the body. That radioactive part of the fluid is radioactive. That radioactive particle decays by beta minus emissions, creating positrons. Those positrons interact with the electrons in whatever the site we're trying to image. The machine then captures the light from the electron-positron annihilation, and then computers do calculations to show where the light came from, and thus can take an image of the inside where this radioactive particle was. And in general, this may be an active site for cancer or something like this. Well, the fact that the fluid that's pumped into the body is radioactive means you can't just have a jar of this radioactive fluid sitting around in a hospital waiting for a patient who needs a PET scan. And the reason is, let's say you were able to save it over a long period of time. That means its half-life is very long. It lasts a long time. It doesn't decay that often. Well, that's good for saving it. However, if we're putting it in a patient and we want that fluid to decay and create positrons, well, if it's got a very, very long half-life, it's going to take forever to decay into positrons. So what you need is a fluid that decays very quickly to create the positrons very quickly, so we could take the test in 30 seconds or a minute or whatever and get the patient out of there. But if the half-life is short to allow for that to occur, you can't save the fluid in the hospital because it decays away way too quickly. So it's up to a medical physicist or a chemist to create that molecule, to create this form of glucose, this radioactive form of glucose. And so you may want to know, well, okay, if I create it, the patient's going to be in the hospital in 2 hours, so I need this amount of it to last or to be around after waiting 2 hours. So how much should I make now such that in 2 hours I'll have enough for the patient to use? This is the type of calculation that is done to figure that kind of stuff out. So it's a very, very powerful model, and it works, and it actually is a good model of predicting radioactive behavior, which is very interesting because radioactive behavior is very probabilistic. It's random. As I said, the fact that this half-life thing works the way it does, that is to say, if you wait one half-life, half of it goes away. Well, why did this half go away and the other half didn't go away? In other words, let's say we split the material down the middle and you had a left side and a right side, and it just so happens that it's all the right side particles that decayed. Well, why isn't those decayed in 8 days, but the ones on the left didn't decay? They just sat around and did nothing. What is it about the left ones that is different than the right ones? Nothing is different. And in fact, you then wait another 8 days, half of the ones that are still on the left side still won't decay. So you may have, if you're staring at one particular radioactive particle in the sample, you may wait 1,000 years and never see it decay. But you look at its neighbor, it may decay after the first 2 days. But they're all the same particles. There's nothing different about them. So while there is this probabilistic nature, I know half of them will be gone. I don't know which half. And I don't know why that half chose to decay while the other ones didn't decay. It's a weird mix of very powerful predictive properties. I know this equation works, and I can tell you without a doubt that within a tolerance of error, this is exactly how much sample you're going to have if you wait this long. What I can't do, however, is say which parts of that sample will stick around. I can't tell you, oh, if you stare at this particle, this one definitely will decay. I can't say that at all. So this is one of those very quantum mechanical type properties that there's a lot of predictive power, but it's all probabilistic. I can't tell you exactly what will happen, but what I can tell you is very, very accurate. So let's do an example, or maybe a couple of examples, of how a problem with radioactive decay may work. Example. How long will it take for 30 grams of radon, it's Rn, and let's say it's radon 222, to decay down to 7.5 grams. Now, let's say I give you the half-life of radon happens to be 3.82 days. 3.82 days. Okay. So, how do we solve a problem like this? I'm actually going to show you there's two ways of doing this. There's the normal, mathematical, rigorous way you will almost always do it. And then I'll show you a shortcut method if the numbers happen to work out very nice. Okay? And of course, this is a classroom environment. A lot of times the problems are theoretical in nature, and so the problems are made and created in such a way as to make the numbers nice. If you're out in the field or in the lab, you probably are not going to have the nice numbers to be able to use the trick, but I'll show you anyway, and you could either use the trick when it's allowed or not use the trick ever and just learn the appropriate way to do it. So, what's our equation? N is N naught e to the minus lambda t. All right, what do I know? Well, let's see. I know N naught is the amount of sample I have to start with, which is 30 grams. N is how much I want left after I wait, which is 7.5 grams. What else? The half-life, T1 half, is 3.82 days. And I know, of course, lambda is 0.693 over natural log of 2. Natural log of 2 over T1 half. Okay, which I could go ahead and calculate while I'm here. That's 0.693 over 3.82 days. So because I'm using days as the units of half-life, the time I'm about to calculate is also going to be in days. Just remember that. So from this I get 0.1814. All right, and what is it I'm looking for? T. I want to know how long do I have to wait. All right, so let's plug our numbers in. 7.5 equals 30 times e to the minus lambda, which is 0.1814 times t. All right, so here I have an equation. I'm trying to find t, but t is in the exponential. How do I get to the variable that's inside of an exponential? Well, just as is usual, and I'll do this as an aside, when you have some equation that's 2x equals 10, and I say, I want to know x, how do I calculate x? We all know you divide by 2 on both sides, and you get x is equal to 5. But I ask you, why do you know to divide by 2? If what I want is x, but I tell you 2 times x is 10, well, you don't need 2 times x. You just want x. So to get rid of the fact that you're multiplying the x by 2, you do what's called the inverse operation. So instead of multiplying by 2, you do the inverse operation of multiplying by 2, which is dividing by 2. But if you do it on the left side, you also have to do it on the right. Well, here, what we're going to do is we have this exponential thing, the exponential of t. Something times t, but there's a t in the exponential. But I don't want exponential of t, I just want t. So what I'm going to have to do is do the inverse operation of an exponential. Okay, before I do it, let me get the exponential by itself. So of course, I'm going to divide the 30 over. So 7.5 over 30 equals this exponential. And now we see, okay, I don't want the exponential of t. Do the inverse of an exponential. What is the inverse of an exponential? The natural log. So, if I want to get rid of the exponential, I do the natural log of it, and that'll cancel the exponential. But if I do the natural log on the right, I have to do the natural log on the left as well. So what happens? I have natural log of 7.5 over 30 equals, natural log cancels the e, and I get minus 0.1814 times t. Alright, so what's the natural log of 7.5 over 30? This is negative 1.386 equals negative 0.1814 times t. And of course, we solve this for t. And we get that t is equal to 7.64 days. And there we go. So here we happen to have a problem where instead of trying to find how much of the substance we will have or how much of the substance we started with, we're looking for how long does it take. It's just one of the unknown variables. So we start with our equation, write down everything we know. This is the general thing you do in physics. Write down all the knowns and unknowns from your problem, and then fill it into your equation and solve for whatever's left. In this case, t was the thing I didn't know. So I got everything with t on one side, all the other numbers on the other. That left me with an exponential function. To get rid of the exponential, I took the natural log of both sides. And then I did the normal algebra stuff you do to get t by itself, and I got an answer, 7.64 days. Now, what's the trick? What trick was I talking about? Let me rewrite the question. There it is. How long does it take for 30 grams of radon to decay down to 7.5 grams, given that the half-life for radon is 3.82 days? Here's the trick. If you find that the amount of time, or, in this case, the amount left over is a half multiple of the original amount. So notice we started with 30. If you divide 30 by 2, you get 15. So to go from 30 down to 15 is one half-life. Okay, then if you divide 15 into half, you'll get 7.5. So that's another half-life. So from 30, half of that is 15. 15, half of that is 7.5. And notice, that's what I want. I only want 7.5 grams left. 7.5 happens to be a multiple, a half multiple of 30. In fact, what it says is, if I wait 2 half-lives, I'll go from 30 down to 15, and then from 15 down to 7.5. So this tells me, wait 2 half-lives, which is 2 times the single half-life of 3.82 days, which of course is 7.64 days. Our original answer. So this is very nice. If you see that the amount remaining is a half multiple of the original amount, then you know the time you're going to wait is some multiple of the half-life. So all you have to do is keep dividing by 2 until you get the amount you want. So for instance, let's say I start with 80, and I want to know how long do I wait to be left with 5. Let's find out what happens. Is 5 a half multiple? Well, 80 divided by 2 is 40. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. Aha! So I could go from 80 to 5. How long do I wait? Here's one half-life, here's a second half-life, here's a third, and here's a fourth. So I would wait 4 times the half-life to get down to 5. So this is a nice trick to do the calculation very quickly. But it only works if it's a nice, even half multiple thing. If I went from 30, and I said, how long will it take to get down to 5? Does this work? Well, let's see. 30 divided by 2 is 15. 15 divided by 2 is 7.5. 7.5 divided by 2 is 3.75. Uh-oh. It didn't get to 5. So I can't do this trick to figure out how many half-lives do I wait to go from 30 to 5. So because of that, this original method is the real method for solving these problems, because this method will always work. This shortcut method works if the amounts are created to be exact half multiples. Okay? So what I would say to you is this. If you've gotten sufficiently comfortable with these problems, then when you see one of these problems, see if it falls into the shortcut method. Divide it by 2 and see if you could get from the original amount to the amount you're looking for. If it does go in evenly, then do the trick. If it doesn't, then you better work it like this. If, however, you're not comfortable with this, you're not very well practiced, then just use this method and don't worry about the shortcut method at all. Because if you try to use the shortcut method when it's not feasible, you're going to get the question wrong. If you use this method, and you do it correctly, of course, you will always get the question right. So that's my hint to you. This is the way to do it. This right here is the big equation. This is how you're going to solve the problems. And so get good at using it. Now notice this example asks you to calculate t, the time. I could give you different questions that ask you for any of the other variables. I can say, what's the decay constant for radon 220? And then I give you some information. Well, in that case, you'd be calculating lambda. Or I can say, how much uranium-235 did you start with if after waiting 32 years, you now have 15 kilograms left? Well, in that case, you'd be looking for N naught, the amount you started with. If I say, how much plutonium will you have if you wait 4 half-lives? Well, you'd be looking for N. How much do I have if I wait a certain period of time? Okay. So there's different ways of asking these questions, but they all boil down to this one single equation. It's just which variable are you solving for in the algebra. So that's all I have for you here. I will be posting a nice little worksheet with some practice problems on them. So be on the lookout for that, and I will probably post a homework just to ask you to do a few on your own, just to turn in for a grade. But if you have any questions, of course, feel free to email me if there's something confusing or you just want to make sure you're doing it correctly. But at the end of the day, what you're going to find is any of the questions I give you will boil down to using this equation, solving for one of these variables. The only thing to keep in mind is the units of time we're talking about. Make sure that the units of t, the amount of time you wait, and the units of half-life are the same units. If they don't match, then you're going to have to convert one of them to be the same as the other. So if the half-life of uranium is in days, but I'm asking you to wait months, then you may want to convert months to days. How many days are there in a month? And then just convert the time waited to days instead of months. So now half-life and time waited is in the same units. All right, anyway, that's all I have for you for this video. Until next time.